in this video we'll review the stresses that we have covered in the mechanics of material and the Mohod circle. So we classify the stress into two categories. One is a normal stress and second is a shear stress. Normal stress is further classified as the axial stress and is represented by symbol sigma and is given as the force upon area. Depending upon the force F, it can be compressive or it can be tensile, and area you have to select as a minimum resisting area. Second type of a normal stress is produced due to the bending. That will be called as the bending stress. For bending stress, you have to use the flexure formula, and bending stress is given as sigma B is equal to M multiplied by Y divided by the second moment of area. M represents here the bending moment, Y represents here the distance of the fiber where you have to calculate the bending stress, and this distance you have to measure from the neutral axis. The bending will be either above the x-axis, y-axis, above z-axis. So if you have a bending moment above the x-axis, then you have to take the moment of inertia above the x-axis. If it is above the y-axis, then you take the moment of inertia above the y-axis. In the axial stress, that is the compressive and the tensile stress, the fiber length will increase. In the case of the bending stress, the length of the some fiber will going to increase and length of the some fiber will going to decrease. So there is a continuous variation of a bending stress over the cross section. As far as the axial stress is considered, it is uniform value. Shear stress we can define when the fibers will slide over each other. That will be called as shear stress. Shear stress is due to the direct also. So first classification is based on the direct shear. That is represented by tau is again the force upon area. Now this formula is force upon area as well as this formula is also force upon area. So how we distinguish? The force and area must be perpendicular to each other. Then it will develop the normal stress, and if the force and area are parallel, in that case we have a shear is produced. Second type of shear produced is due to torsion. So if the shaft is subjected to torque, then we have a torsional shear stress is produced, and this value of torsional shear stress we can obtain from the torsion formula, which is given as tau is equal to torque multiplied by radius of the fiber where you are interested to know the shear stress divided by the polar moment of inertia J of the entire cross section. In the case of SFD and BMD, some portion of the beam may be subjected to moment as well as the shear force. In that case, we have complementary shear stress is produced due to bending. So you will call it as bending shear. And the value of the bending shear is given as the shear force is equal to V multiplied by Q divided by the second moment of area, that is moment of inertia, multiplied by thickness T. Q here is a slightly complicated to calculate in the case of complementary shear. Two stresses we'll discuss first. One is the direct tensile stress and the compressive stress. Suppose we have given here one bar of uniform cross section, and this point represent here the centroid of the given cross section, and through this point if the force is applied to the bar and is outward, that is this force is outward force, similarly this force is also outward, both time it is passing through the centroid of the cross section. So when the force F is applied, the fibers of the component tend to elongate under the external load. So if you see the first figure and the second figure, in this case there is a elongation of the fiber in the same direction of the force is equal to dl. So F represents here the external force, A represents the uniform cross section, then we have a tensile stress is produced. So tensile stress will represent as sigma T is given as force upon area. This time the force and area they are perpendicular to each other. Suppose this bar has a circular cross section, then we can show the stress on this part. Since this section is perpendicular, everywhere the stress is remain constant. If you consider the state A or state B, everywhere we will get a uniform state of a stress. Even at C here, we have same state of a stress, that is a tensile stress. So this value is same as sigma t, and if we want to represent here the state of a stress, then we can represent the plane state of a stress with one normal value, that is outward. This value was taken as sigma x is same as equal to force upon area, and you have to show here reactive stress also, that equal to sigma x. So this one is the state of a stress at point A as well as B as well as C or anywhere in this cross section. That is the stress distribution in this case is a uniform stress distribution. Again consider the same bar, but this time the force is passing through the centroid in opposite direction. So due to this force, which one is basically the compression force, the length of the fiber will going to shorten due to the external load F. The stress developed in this component will be called as the compressive stress, which is taken as negative value. So in this case, due to application of the compressive stress, there is a decrease in the length of fibers, that equal to dl, and this value of the stress will be called as the compressive stress. We can represent it by sigma suffix c, and is same as again the force upon area. For calculation purpose, this value you have to take as a negative value, and this one nature is compressive. Again we consider here the circular cross section. Then at any point A, B, C, we have a same state of a stress, but this stress is taken as a negative value. So if I want to show you state of a stress at point A, B, C, I have to show the arrow inward. So this space is same as this space, and this value is same as sigma x, which you have to take as a negative value of sigma c. So in tension you have to take the positive, and in compression you have to take it negative. If the cross section is not uniform, in that case you have to take the minimum cross section, which is resisting the given external load is equal to F. Now we'll discuss here the bending stress, which is purely due to the bending. For this one we'll consider here a circular cross section of a bar which is subjected to bending. So we'll set up our axis system. This axis is same as equal to x axis. Vertical axis will take as y axis. So axis system will fix up at the centroid of the cross section, and the portion which protrude is along the z axis. Suppose this bar is subjected to uniform bending moment equal to m, and we'll consider the moment about the x axis. So this moment we are representing about the x axis, that will be called as mx. So there is a reactive moment will takes place about this axis, which one is again about the x axis, is equal to mx. We can represent the bending moment by using the arrow, or we can represent it by vector. Since this vector is along the x axis, so we can show here the vector is acting along this one. So this one is also a representation of a moment in the vector form. So the direction of arrow is for right face is anti-clockwise. So the top fiber will come in compression and the bottom fiber will be in tension. So this was the enlarged section again of the same circular bar of diameter equal to d. Let's call this one is the neutral axis, which is the horizontal direction. As shown in the figure here, we have vertical axis equal to y. So this one is our vertical axis is y. This one is horizontal axis equal to x. And if you are familiar with the flexure formula, the flexure formula is given as m, that is the bending moment, divided by moment of inertia I. If you have a bending moment about x axis, you have to take the moment of inertia about the x axis is same as equal to the bending stress divided by y. Now you have to select the fiber here, whether the fiber is on the top side or the bottom side. Suppose you select the fiber at this point here, then you have to select the value of y from the neutral axis. So on this fiber we can calculate here the bending stress. For the given cross section, the bending moment will be uniform, Ix will be uniform, only the value of y will change. Now if you take the edge view of the same circular section, and as per the given bending, the top fiber will be in compression, so that value will show on the opposite side. Since the y value is maximum on the top fiber, the value will be maximum, and it's a linear distribution. So this value will go on decreasing. Exactly at the neutral axis, this value will be equal to 0. Then we come to the bottom side and the stress will go on increasing. This will be the stress in tension. So in this position, we'll get the maximum stress on the outer fiber. If you are interested to know the state of a stress at a point A, which is on the top fiber, state of stress on the fiber which is at neutral axis, B and C will consider at neutral axis, and at point D we have bottom fiber. So this stress corresponds to A, this stress corresponds to B and C, that is equal to 0. So the stress due to bending at a neutral axis is always equal to 0, and this stress corresponds to D. Naturally here, if I want to show the state of a stress at point A, then I have compressive stress, so I will show the arrow is inward. And for circular section on the top fiber, the maximum value of y will be equal to d by 2. So at this point A here, we have y is equal to d by 2, and therefore we have bending stress will be equal to sigma b is equal to mx. Now this value is m is remain constant here, so it is simply mx, moment about the x-axis, divided by ix multiplied by y, and this time we have y is equal to d by 2. As far as the moment of inertia for circular section of diameter equal to d is pi by 64 d to the power 4. So we can very well calculate the value of sigma b. We have m into d divided by pi by 64 into d to the power 4 multiplied by 2. So this 32 will come in numerator, and you will get the bending stress approximately equal to 32 times m divided by pi into dq. And this value you have to take as a negative value. As far as B and C is considered, you don't have to show any stress. So this one is the same state of a stress at point B and C. And at point D, we have the tensile stress is produced. Tensile stress is always shown is outward, and this value of bending stress is same as equal to 32 m divided by pi dq. Anyhow, you are interested only in the positive value. We can select here the absolute value, and we can select the positive sign. So depending upon the direction of moment about the x-axis or y-axis, we have a plane bending. So this is a discussion about the bending stress for uniform cross section. Our cross section can be circular or can be rectangular. Only the formula for I will change, and the distance of fiber of the top and bottom for rectangular and circular cross sections will be different. Every time you have to measure the distance y from the neutral axis, where the bending stress will be equal to 0. This distribution is a linear distribution as seen from this equation, because for any section the moment is always remain constant and moment of inertia is also remain constant. So whenever a machine member is subjected to bending moment, tensile stress develop on one side of the neutral axis, and the compressive stress will develop on the other side of the neutral axis. Therefore the outside fibers are in tension and the inside fibers are in compression. Bending stress at any point here is sigma b is equal to m divided by I multiplied by y. So our distribution is a linear, and the stress is proportional to the distance of the fiber from the neutral axis, and it is the maximum if the fiber is farthest away from the neutral axis. So tensile and the compressive stresses are the axial stresses. Even the stress produced due to bending moment is the axial stresses. Now we'll discuss here the shear stresses. In the shear stress, the first we consider the direct shear stress. So we'll consider here the two plates are joined together with the help of a rivet. So this one is a rivet, and let's say it is subjected to the load is equal to F. This value of F and this value of f are acting in an opposite direction, total value will be equal to 0. That is, summation of fx will be 0. So in this case, the rivet is subjected to the direct shear stress because when the external load is acting on the component tend to slide the adjacent plates with respect to each other. So sliding of the plate will take place at this area and this area. So bottom rivet will go to the left side and the top rivet will try to go to the right side if its failure is due to shear. So in this case, the adjacent planes will try to slide over each other as shown in this figure. And there is a development of a shear stress here. So if I separate the two half of a rivet, so we can represent here the two rivet in this fashion. And it will develop a shear stress here. For the top rivet, the force is acting in the rightward direction. In that case, we have shear stress is produced. This value of the shear stress is equal to tau, and the corresponding area will be equal to pi by 4 into d square. Similarly, for bottom rivet, the force is exerting on the left hand side, that equal to F. So the shear stress will produce on this circular cross section, which is equal to tau multiplied by pi by 4 into d square. So tau represent here the direct shear is same as equal to force upon pi by 4. So we have 4 times of F divided by pi into d square. If the rivet will break into two pieces, it is called as a case of single shear. In general, the average shear stress is given as force F divided by cross-sectional area. If you observe the force and the cross-sectional area, this time the force and the cross-sectional area are parallel to each other. So in the case of shear stress, the force F and the cross-sectional area, this time the cross-sectional area is same as the shear area, are parallel to each other. If they are perpendicular, then it will be called as normal stress, and if projected, it will be called as the bearing or the crushing stress. Suppose the top plate and the bottom plate are connected by means of one middle plate. Again, we are using here the riveted joint or bolted joint. In that case, we have to show the rivet or a bolt. So this one is the head of a rivet. This one is also the head of a rivet, and you can see the body of a rivet. Suppose this joint is subjected to external force. Let's say middle plate will be pulled to the right by the force is equal to F. So this force is distributed equally between the top plate and bottom plate. So we have to show the force here will be equal to F by 2. And this force is also equal to F by 2. Every time you have to check out here the summation of Fx or Fy for the given arrangement must equal to 0. That is the condition of a static. So this part will go towards the F by 2 that I will show here. So this one is the head of a rivet. Then this portion is pulled to the left by the force is equal to F by 2. And the shear stress will act in a rightward direction. So in this case, the shear stress will be equal to tau multiplied by area is a shear force. So we have F by 2 is same as equal to tau multiplied by area. That is, we have shear stress equal to F divided by 2 times of area. If you see the middle portion here, the middle portion will show somewhat like this. In this case, the force will pull it to the right, that equal to F, and this value will be equal to tau multiplied by area, as well as this value is also equal to tau multiplied by area. For this case also we can write here F is equal to 2 times of tau multiplied by area. Again we get the same answer, that is we have tau is equal to force upon 2 times of area. So this one is representing the case of a double shear, and at bottom if you again do the analysis, then we can find here the bottom rivet can be shown in this fashion. The force F by 2 pull it to the leftward. This force is resisted by the shear, which is equal to tau multiplied by area A. This case is same as this case. So in this case, we have tau is equal to F divided by 2A. This one is called as the double shear. That is, if the rivet will fail into 3 pieces, then it will be called as double shear. So this one is the example of a direct shear. Second type of shear is called as torsional shear stress. So we'll consider here one shaft. Again, at the cross section centroid, we fix up our coordinate system x and y. X is horizontal, y is vertical, and along the length we'll set our z axis. So torque is applied in the xy plane, that is above the z axis. So this one is representing the torque is equal to T. This torque is since applied along the z axis is represented as mz. So mz we normally call as the torque, that is the twisting moment, and if we have a bending about the x axis, then it is represented by mx, or if we have a bending of this shaft about the y axis, it is represented by my. So mx represent here the bending moment about the x-axis, my represents the bending moment about the y-axis, and mz represent here the twisting moment about the z-axis. That is also called as torque. Due to the application of the torque here, all the fibers will be get rotated due to the torque in the same direction of torque. So for balance here, I have to show here one reactive torque which will act in the opposite direction, that will be equal to T. The stress induced in this machine member to resist the action of the twist is called as torsional shear stress and is represented by tau, is given as torque multiplied by radial distance r from the fiber of the axis of rotation divided by polar moment of inertia equal to J. So the value of r represent here the distance of fiber from the axis of rotation. From the given equation we can conclude here the shear stress is directly proportional to r, as the value of torque and polar moment of inertia is remain constant for uniform cross section. So as the value of r will go on increasing, the shear stress will also go on increasing. In this case also we have linear distribution which is almost similar to our bending stress distribution. Only thing that in the bending stress we have positive and the negative value, that is the compression and tension. In this case only the shear stress is produced. So this one is the axis of rotation, that is this point is the axis of rotation. We call it as center C. Now the radial distance will go on increasing, the shear stress will also go on increasing. So in this case this fiber will be the outer fiber. For outer fiber we have radius r, that is the radial distance r will be same as equal to capital R. So if I put here capital R, I will get the maximum value of the shear stress. So on outer fiber we have tau is equal to torque multiplied by r divided by J. So on the outer fiber we can show here the shear stress is maximum and will be 0 at the axis of rotation. So we'll consider here one section anywhere. So this one is a section at any distance equal to x, and we'll consider here the top fiber at a distance equal to r, which is represented here, that equal to a. This one is representing as b. So this b as well as this c, they are again at the outer fiber. One fiber will consider at bottom, that is this fiber will consider at bottom, that equal to d. So these are the fiber position on the outer radius, that equal to capital R. As shown in the figure here, we have this one is the direction of torque T. So if you want to show the shear stress, you have to show the shear stress in the same direction. So this one is the direction of shear stress at A. This one is the shear stress at B in a downward direction. In this case the shear stress will be rightward, and here the shear stress will be upward. So we have shear stress at A is same as shear stress at B, is same as shear stress at C, is same as the shear stress at D, and is equal to the maximum value of the shear stress, that is torque multiplied by R divided by J. For solid shaft, we can take the polar moment of inertia is equal to pi into d to the power 4 divided by 32. So we can put for j as pi d to the power 4 by 32, or we can put as d by 2. So we can calculate the shear stress at any point A, B, C on the outer fiber. That will be equal to torque. Radius we can write as d divided by 2, and polar moment of inertia is pi. 32 will shift in numerator and divided by d to the power 4. So one of the d will be get cancelled and we left here q, and we'll get the equation of torque is equal to 32 by 2 is equal to 16 into torque divided by pi into d cube. Whereas the bending stress is given as sigma b is equal to 32 times m divided by pi into d cube if we are using a circular cross section. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.